So we've already seen that the standard deviation is a measure of how spread out data is, and we've seen how to compute it, and we know that data with a large standard deviation means it's more spread out than data with small standard deviation. In this video, I want to show you that you can use the standard deviation as a sort of a ruler that can help us compare two different quantities that have different units. So we'll look at this example here. This says Dylan was an excellent student, athlete at Framingham High. In soccer, he scored 90 goals during his 4 years at the school, and it turns out that when all the data was gathered on top scorers throughout FHS history, the mean career goals was 75 with a standard deviation of 10 goals. He's also an accomplished mathlete on the math team, and his math IQ was measured to be 130. And the IQ data on all mathletes throughout FHS history showed that the mean IQ was 120 with a standard deviation of 4 points. And so the question is, comparatively, is he better at soccer than he is at math, or vice versa? So this is one of those questions it reminds you of those fun questions you might ask where you would say something like, I don't know, was Michael Jordan a better basketball player than Lionel Messi as a soccer player, right? It can be sort of impossible to make those arguments or to make comparisons because two different contexts, right? And there's no real way to compare those two things because they're from completely different, from two different sports. But the standard deviation is one way you can sort of make sense of that and actually say something meaningful about who's better at what. And so that's what we're going to do here in this problem. So in order to compare his performance in soccer with his performance in math, let's make two number lines. One that will measure how good he is at soccer and one that measures how good he is at math. So what I'm going to put at the center of this number line is the mean number of career goals that were scored by a population. Okay, so that's important. The mean career goals of 75 means that you looked at a population of goal scorers, or top goal scorers, throughout FHS history, and the average was 75. Now his score was or the number of goals he scored was 90. So I'm going to put that out here. Okay, so now what we're going to do is we're going to see how many standard deviations away from the mean his record was. So we're told that the standard deviation is 10 goals. So I'm going to jump from 75 to 1 standard deviation. So if I jump 1 standard deviation, which I just did, that brings me to 85. Okay, so I'm not quite at his record. Now I can't jump a whole nother standard deviation because that would bring me to 95, so I'm going to just jump one more half. So that's 5, which is a half a standard deviation. Okay, so I'm going to write this out explicitly. He is his 90 goals is 1.5 standard deviations above the mean. So his performance of 90 goals is 1.5 standard deviations above the mean. Okay, so that's just again, we just treated the standard deviation like a ruler there. Let's go see how we did in math. So in math, the mean IQ, the mean math IQ, whatever that means, I obviously made this up, but the mean math IQ is 120. So that's going to go here. And actually, I'm going to put the symbols in just to remind you. That's the symbol for mean, and up here. Okay, so there's our mean. Now, his IQ was 130. So let's put a 130 out here. So let's see how many standard deviations above the mean he is. Now the standard deviation is 4 points, so I'm going to jump 4. And by doing that, I've just jumped 1 standard deviation. And that gets me to 124, right? So I can jump another one. If I jump another one, that brings me another 4. That's another standard deviation. And that brings me to 128. So at this point, if we're keeping track, I've jumped 2 standard deviations. Now I can't jump another full one, so I'm going to jump a half one, adding 2. So that's 1/2 standard deviations. And that gets me to the 30. So that says that his performance, or I guess performance is the wrong word. Let's just say his math IQ. His math IQ is 2.5 standard deviations above the mean. So what can we conclude at this point? Well, notice that even though the number of goals he scored in terms of raw numbers, so that was 15, he scored 15 more goals than the average for that population. His IQ was 10 points higher than the mean IQ for math. In terms of raw numbers, it looks like he might be better at soccer because 15 is bigger than 10. But in terms of standard deviations, his performance in soccer is not as good as his math IQ is, because his math IQ is more standard deviations above the mean, which just tells you that his math IQ is a more rare phenomenon than his performance was in soccer. So I mean, 1.5 standard deviations above the mean is good, but it's not as good as being 2.5 standard deviations above the mean. In other words, he's better than, or I guess we'll say smarter than, a greater percentage of the population of mathletes than he is as a performer in soccer. Okay, so our conclusion will be that comparatively, he is better at math than he is at soccer. Since his math IQ is more standard deviations above the mean than his number of soccer goals. Okay, and that word comparatively again is important because it just means we're comparing his performance in soccer with the entire population of top scorers, and he is pretty rare, right? 1.5 standard deviations, that's above the mean, that's good, but it's only 1.5 standard deviations. Whereas in math, 2.5 standard deviations, it turns out, is a big jump. So he is well above average in math, according to this made-up example. So the point of this was just to give you a sense that the standard deviation can be used as sort of like a ruler, and it allows you to compare two quantities with different units. But of course, you need to know the mean, and you need to know the person's or their individual data value, and then you use the standard deviation to measure how far away that is. Now, in the next video, we'll look at more, or the next slide rather, we'll look in more detail about what this computation actually entailed, so that we don't always have to draw pictures like this. But hopefully this at least laid some groundwork for talking about standard deviation as a way to compare. So since we're using the standard deviation as a measuring tool, we want to look at a formula that will tell us the number of standard deviations a value is away from the mean. That way we don't have to draw number lines. And that's what a z-score is called. So you'll hear the word z-score a lot. A z-score is just how many standard deviations a value is from the mean. Okay, that's all a z-score is. So let's look from above. I'll actually do the example we just looked at, and then we'll talk about how to just formalize the process. So from the example we just looked at regarding soccer and math, the z-score for soccer, for Dylan's 90 goals in soccer. So how did we get that? Well, if you think about it, we needed to see how many times the standard deviation, which for soccer was 10, went into the distance between his performance, 90 goals, and the mean, which was 75 goals. So we took that distance, 90 minus 75, right? That's 15. That was the distance between those two numbers, and subtraction gets us that distance. And then we saw how many standard deviations went into that, which implies division. Okay, so 90 minus 75 was a distance of 15, and we saw that jumping using 10 as a jump length, 2.5 of those 1.5 of those 1.5 of those went into that distance. And again, for math, we saw that his score, or his IQ, was 130. The distance between that and the mean is 130 minus 120, which was 10. That was that distance. And we want to see how many standard deviations went into that, and that was, we were doing jumps of 4. So this produces 10 divided by 4, which we found was 2.5. Okay, so that will tell us how to compute the standard deviation, because if you look in both cases, all we did was we took the score. So I'm going to use the variable x, right? The score, we subtracted the mean, and we divided by the standard deviation. So I'm going to use the letter S. Okay, in both of those cases, that's all we did. Okay, and so now we can formalize. So the standard deviation, or the z-score rather, again, how many standard deviations you are away from the mean, is your data value minus the mean divided by the standard deviation. So there are different symbols for the standard deviation. I'm just going to use S for now. Okay, so again, that's our standard deviation. So you have to know that. I mean, the standard deviation has to be provided to you, or you have to compute it. That, of course, is our mean, and that's our data value. So this is a formula we'll just use. I did my best here to try to get you to understand it, but if I failed, at least memorize it, because you're going to need to use it. You're going to be asked to find z-scores often. Okay, so that is the standard deviation. That is a z-score, how many standard deviations you are from the mean. You should note that, and we're going to look at a few properties in a second, but just note it has no units, because 90 minus 75, the units there were goals. The standard deviation was 10 goals, and so when you divide, you have no units. Same here. The units here were points. The standard deviation was measured in points, so it's unitless. And we'll look at a few other properties on the next slide. So the three properties we'll just take note of for the z-score is the mean always has a z-score of 0, because if z-score is the distance between the mean and the data value, then the mean is 0 units from the mean. So the mean always has a z-score of 0. Okay, that's one important point. So that's always. Data values below the mean have negative z-scores. Okay, so a negative z-score basically just tells you that your data value is below the mean. And positive z-scores indicate your data value is above the mean. So just to save on some writing, let's just put in parentheses above and positive. And lastly, the last property is that standard deviation has no units. Or the z-score, sorry, that was wrong. Standard deviation does have units. Z-score has no units, which we indicated before. Okay, so there are the three properties of z-scores, and we'll take a look at some examples next. So let's look at an example. The heights of American women are approximately normal, with a mean of 64.5 inches and a standard deviation of 2.5 inches. So we're going to talk in a minute what it means by saying, what it means to say that the heights are approximately normal. But for now, all we care about is the z-score. So the mean is 64.5 inches, so we can indicate that usually with the x with a bar over it. And the standard deviation is 2.5 inches. So you'll often see that the standard deviation of a population is given by that Greek symbol. Okay, so I'm just going to indicate that sigma. Find the z-score for a woman 68 inches tall. So the z-score is just the difference between her height and the mean divided by the standard deviation, which is 2.5. Okay, now if you do this on your calculator, you end up getting 1.4. Okay, so a z-score for a woman 68 inches tall is 1.4. So to really emphasize what this means, I'm going to say this means that a 68 inch tall woman is 1.4 standard deviations above the mean in height. Okay, and you'll learn, especially when we talk about the normal model, you'll start to think in terms of standard deviations. So if I said someone was 3 standard deviations above the mean for height, you're going to learn that that means that that person is comparatively very, very tall. And someone who's like -3, who has a z-score of -3, then they're very short. So let's just do this next example. A woman who's 60 inches tall, her z-score would be, so her score is her height is 60 inches minus 64.5 divided by 2.5. This time, notice we're going to get a negative because 60 minus 64.5 gives you a negative number, and here you get negative 1.8. Okay, and so this means that a 60-inch tall woman is 1.8 standard deviations I don't know why I abbreviated at the top and didn't here, but whatever. Standard deviations below the mean. Okay, and again, I mean that just means she's shorter than average, and the 1.8 tells us something about how much shorter. Okay, and again, you'll start thinking in terms of units. So this is going to lead us into the normal model, which involves the standard deviation and the mean, and we're going to use this concept to make comparisons between individuals with respect to the overall population that they come from.